Hello, everyone. Welcome to today's seminar. Today we have Karel Van Bockstal from Ghent University, Belgium, and Karen is going to talk about inverse source problem in time fractional diffusion equations with non-smooth solutions. Karel, thank you so much for accepting our invitation. It's very good to see you here. So you may start whenever you're ready.
Okay, thank you for the kind introduction.
Thank you.
So indeed, I will speak about my work on inverse source problems in time fractional PDEs. So we discussed already a bit, but I'm affiliated at Ghent University in the Ghent Analysis and PD Center led by Professor Ryzansky. And this is a joint work with Dr. Hendy. He works currently at Ural Federal University. So I will start with the introduction on the topic, and I will explain the main idea on the basis of classical heat equation. And the goal is, in fact, is to show for the inverse problem under consideration the existence of a unique solution in the case of exact data. And I will also show some results of numerical experiments, and there are definitely possibilities for future research. So the problem setting is as follows. So omega is a bounded Lipschitz domain in d-dimensional space. Boundary is denoted by partial omega, and final time is denoted by q. So the space-time cylinder is denoted by qt, and the boundary by sigma t. And in this presentation, I consider a general second order differential operator with time-dependent coefficients. So A is a Hivin tensor, so coefficients are space and time-dependent. And what's important here is that the coefficient in front of u only depends on time. I will try to explain later why this assumption is necessary in our approach. So when it's assumed that A is a symmetric tensor. So it's problem is the fractional PDE setting, and we consider Caputo type of derivative of order beta. So beta is between 0 and 1. The derivative is defined here, time derivative outside the integral, and we have u minus u0, and we have in the denominator the gamma function. So this is the definition. So let's take a look at the formulation of the problem. So we have Caputo derivative, here the operator L of u, and on the right hand side we have the known part of the source. It's inverse source problem, and we are looking to recover time-dependent part of the source. So the space-dependent part is Hivin, and we try to find the part h of t from this integral measurement. And measurement is on the complete domain omega, and is denoted by m of t. On the right-hand side, we see we have also a possibly nonlinear function, f of nu, also can depend on the independent variables. And you see here an additional integration in time. Also, this integral is needed. So the target for future work is to be able to consider f of u in the right-hand side, but at the moment we still need this integral and also Neumann boundary conditions. So in fact, if you also look at classical heat equations, we will see later, this measurement is well working in connection with the Neumann boundary condition. So would be nice if we could get a similar result in the case of the boundary condition. This is not the case yet. So when u tilde 0 denotes the initial data. So this talk is mainly based on this work published in Journal of Scientific Computing last year. So to have good understanding of the approach, I will explain the idea on the basis of the heat equation. And later on, I will give me more details about how to obtain the well-posedness for the fractional PDE. So here, same problem, but heat equation h of t, and here average measurement is considered because I have put here both Dirichlet or Neumann data on the boundary. And here the measurement is denoted by E of t. So what's the usual approach inverse problems to recover h of t is to measure the equation. And with measuring the equation, you mean that you use the measurement to get an expression of h of t. So here you basically multiply the PDE with a small omega with the weight function and integrate over the domain. And depending on the boundary condition, you get a different expression for h of t. And you can find in this paper of Cannon and Lin the expression for the Neumann boundary condition. So from the first term, you get the derivative of the measurement. And when you apply Green's formula, on the second term, you get the scalar product of the gradient with the gradient of the weight function. And on the boundary, you may use the Neumann boundary condition to get a inner product of G and the weight function. So you need to assume to get the expression of h of t, and this is important, that there is a connection between the measurement and the given part of the source. So this integral cannot be to 0 because you need to divide by this scalar product of f and omega. So it's a part of the assumption, and I think it's one of main open problems in inverse problems. What you can do if this integral is equal to 0? So, but we suppose that it's not the case. So to be well defined, this function omega should be h1 integrable, and to belong to this Sobolev space. And for the Dirichlet boundary condition, you can take a look in the book of Prilepko from 2000, where you get this expression in the same way. But what you see here is that there is no boundary term. And this is due to the assumption that the weight function is 0 on the boundary. If this weight function would be non-zero on the boundary and you need to get estimates, then in fact you need H2 regularity and of the solution, which is difficult to achieve. So there's a reason to consider this assumption. You can even put all derivatives on the weight function. So then you get Laplacian of the weight function multiplied with u. And from the boundary condition, you get that then also the additional boundary integral is equal to 0. So in the case that the weight function is in the intersection of these two spaces, you can write down this expression for h of t. So this is the basic idea, is to measure the equation. Then you can use, for instance, results from Volterra type equations to get existence and uniqueness of a solution to the inverse problem. And I have here a sketch for the autonomous Keith equation. So with time-independent coefficients, the operator L is defined here. It's assumed that asymmetric as well, such that it's equal to its adjoint operator. And so in this case, we have a closed formula for the solution using semi-group theory, which is given here. So if you apply the operator L on this formula, you get this expression, and also here when you multiply with the weight function integrate over the domain, you can get an identity, and in fact a Volterra equation of the second kind if this integral, as assumed before, is non-zero. And here I have also used that the operator is self-adjoint to put the adjoint operator and so L on the weight function. Okay, so from the theory of Volterra equations get under these conditions on the data that there exists a unique source, and if you have looking for uniqueness, then you can you have also immediately as a consequence that you will be equal to 0 in the uniqueness proof. So you get the existence and uniqueness of a solution to inverse problem. And this additionally in this paper of 2013 of Professor Stodicka, he showed that you can also use the bond measurement with a semi-group approach to recover h of t. But this approach doesn't work in the case of time-dependent coefficients, and need some other techniques and possibilities to use an energy estimate approach, which I have shown here for a time independent coefficients. But anyway, this approach works fine if you put a divergence of k gradient u, for instance, with a k tensor or a scalar function depending on space and time variable. So if you want to show uniqueness in variational approach, then and it's a linear problem, then it's equivalent with showing that the solution is equal to 0 if the initial data and the measurement is equal to 0. So I've shown you before the expressions for h of t, which simplifies to this form if e is equal to 0. So depending on the assumptions you made on the weight function, you get that absolute value of h of t is bounded by some constant multiplied with L2 norm of the gradient of the function, or L2 norm of the function u. And this estimate you can use to obtain the uniqueness to obtain in fact that u is equal to 0. And if u is equal to 0, then also h is equal to 0. So you multiply PD with a solution, you integrate in space and time. So this bracket here denotes the L2 inner product to obtain this equality. And then on the right-hand side, you apply the epsilon Young inequality. You put small constant on the term with h and the big constant L2 norm of u squared. So this gives this inequality. And then you can fix epsilon sufficiently small. So in the situation that we assume that omega is in H10, we get here the gradient of u squared. This term integral is also on the left-hand side. So if epsilon is smaller than smaller than 1, we have some we get a positive term on the left-hand side. And you can apply the Grunwald lemma to obtain that u is almost everywhere equal to 0. It's in fact so concludes the uniqueness proof. What will be different when you work with fractional diffusion equation is that this information about the L2 norm of u at any time point is not available when working with this type of equations, and this is makes some additional complexity when analyzing fractional PDEs. So in 2015, Riemann, Pre, and Stodicka showed for in the case that the weight function is equal to 1 and for Dirichlet boundary conditions that there is a global and time solvability of this problem. They provide also a numerical scheme for computations. Okay, so let us take a look at literature about inverse problems for fractional equations. So here, operator Alice Autonomous is a paper of Sakamoto and Yamamoto, well-known paper of 2011. There at the end of the paper, they show a stability estimate for the inverse source problem of recovery h of t from the pond measurement. So also, so if you use a pond measurement, then you need to assume that f, the Hive part of the source in that pond, is non-zero. So this estimate implies uniqueness, but they have considered no numerical method to retrieve the missing information. And later in this paper of Wei and Zhang, they considered the same problem in 1D situation, and they made analysis based on the Duhamel's principle. So the formula for solution got a first kind Volterra integral equation and have combined this with Tikhonov regularization to solve the problem. In this paper, the authors considered a different measurement. They considered a boundary measurement on some part of the boundary, and also with this measurement, they showed uniqueness and stability for the inverse problem, and they used Tikhonov regularization to retrieve h of t. And then, in fact, our work is mainly based on this work of Siskova and Slodichka of 2017. In fact, same problem setting, where they show existence uniqueness of a weak solution in case of exact data, but they assumed that or made assumptions on the solution, improving their results, which in fact implies C2 regularity on the closed time frame, so that the function is in the time variable C2, that on the closed time frame. And this is not the case for kappa-2 fractional subdiffusion problem. There you have if you look let's say in 1D to the problem and solve a problem with a separation of a variable, then you can really see that the derivative has a singularity. So this effect, so it's called that the solution has some lack of smoothness. It's well known that solution has some lack of smoothness at the initial time called weak singularity. So it's smooth away from t equal to 0. But the time derivative has a singularity, and it's referred to in this papers already, but in paper of Steins in Science Journal of Numerical Analysis, there is shown that you have this bounds under assumptions on the initial data and the source on the solution. So you give e to the power beta for u, but for the first order time derivative beta minus 1, and so beta lies between 0 and 1. So this shows the unboundedness, and for the second time derivative you get beta minus 2. Later, Kopteva generalized this result to an autonomous operator in 2 and 3 dimensions. So the idea of our work was also to consider this regularity for the solution of the inverse problem. So not that use in C2, but has the correct regularity. Of course, important question here is when you consider integral on the right-hand side, and I will only focus on the special linear case, whether you still have same behavior of the solution. So we solved this problem Fourier method. We got this formula for the solution, and you can see more details in the paper, but you can show that u is uniformly bounded and the time derivative is this bound, so here t to the power beta minus 1. Okay, so this is an important remark. So in our paper, we have designed 2 numerical algorithms based on Rothe's method. It's a time discretization method, and it's one algorithm is on a uniform mesh, and a second one is on a graded mesh. And the scheme on the uniform mesh, in fact, is considered to show the existence and uniqueness of a solution for a non-smooth solution, but there is still a restriction. So the solution can only have terms with t to the power gamma, and gamma should be strictly larger than the order of the derivative. So I'm still looking how to fix to consider this type of bound on the solution, but it's not working yet. So we basically use convolution quadrature. I will show it in a few minutes. And the second scheme on the graded mesh has the advantage to cope better with the behavior at t equal to 0 of the solution, because there are more time points around initial time. In fact, we use the graded L1 approximation for the coupled derivative, and here t to the power beta is included in the class of admittance of solutions, but in fact I have put some solutions, assumptions on the solutions, and to show the convergence of the scheme. So our results are supported by numerical experiments. Important to note is that okay, I hope you still hear me.
Everything is okay. You can.
Okay, thank you. Important to notice that you can rewrite the compute fractional derivative with 8 of the kernel k is defined here, Riemann-Leibniz kernel, and this k has nice properties. This asterisk symbol stands for the Laplace convolution product. So k is L1 integral, is positive. The time derivative is locally integrable and negative for strict positive t. And what's also is important is that it's convex. And these three properties together imply that the kernel is strongly positive definite. So that's a property you can use when analyzing fractional PDEs. So what you see here is the expression of h of t, which you can get similar approaches for the classical heat equation. So idea was to recover h of t from the measurement, integral measurement of u over the complete domain. So you integrate the equation over omega, and to get this expression, you need to assume that this integral is non-zero. To get the convolution of k with the derivative of the measurement, you need that assumption that the measurement is absolutely continuous to over the time derivative inside the convolution. This integral of g follows from divergence theorem. So this is why this Neumann boundary condition is important to get rid of u here and to get just boundary integral of the Neumann function g. And here you see c of t multiplied with a measurement. So we assume that c is only time dependent, such that c comes outside the integral over the domain, and so that you get a product of c with the measurement. Otherwise, there would be an integral of c multiplied with u, and that makes it more difficult to estimate h of t. So this is the right-hand side integrated over the domain. So this is the equation for the source, and it's called the measured problem. And so what we do is reformulate, and we did this also earlier in our research on the determination of for instance, convolution kernels, is to reformulate the inverse problem as a direct coupled problem. So this is a classical variational formulation after multiplying with the test function phi in H1 and applying Green's theorem. So and together this you get from the PD, this equation together with the measured problem from the direct problem in this L of t is product of value with phi of the replicate, and then you apply Green's formula to get these two inner products. Okay, so we look for H in L2, U in L2 0 to H1. So these terms are well defined, and this is in the dual space. Time derivative is to be interpreted in the dual space. Okay, something more about why we have considered the integral of f of u in the right-hand side instead of just considering f of u. So in the classical heat equation, you get when making a stability estimate, a norm of ut squared on the left-hand side. So if you just multiply the PD with a solution, integrate over domain and in time, then you will get this term here. Then in this paper of Kobicha and Yamamoto, they showed in paper in 2018 that you get this estimate for this term. So it's larger or equal to the kernel at finite time divided by 2, multiplied with this L2 0 t L2 omega integral. So the integral from 0 to 8 of L2 norm of ut squared. So you get an additional integral here. If you first decide to integrate PDE and then to test with a solution, then you will end up with a term like on the second equation, so the convolution of k with u, scalar with u, and integrate it in time. And using the strongly positive definiteness of the kernel, you get that this is positive. So also no additional information like here. So this is the real. If you get so this on the left hand side, you need also an additional integral on the right hand side. This is a basic idea, and I have sketched the proof for the uniqueness. In fact, first proof I will show is only working if f is linear in U. And I've put here easier form for L U minus Laplacian of U. So no coefficients. So f is linear. It's a product of U with some given function of x and t. Need some information about the time derivative of g, and it should be L infinity. And so if you want to show uniqueness, you suppose that there exist two solutions. Subtract, consider the differences h and u, and we want to show that this is equal to 0 as I did before. So measurement is 0, g is equal to 0, initial data is 0, and expression of h of t simplifies to this fraction, and here we have the variational formulation. Okay, so if you what we did here is first integrate in time, then choose the test function, and then you integrate again. So this is the reason why you get these three terms on the left-hand side. So in the first integration in time, if you makes it, you get rid of the time derivative and the convolution of k and u at time 0 is equal to 0. So k is strongly positive definite, so this term is positive. So on the left-hand side, you have integrals, L2 norm of integrals of the gradient of u and of u. And so you need, if you want to apply Gronwall lemma, on the right-hand side, you need either or same type of integrals with small constant or an additional integral. And if you estimate h of t, then you, if you do this directly, you would get the integral of the L2 norm. This is not okay, so we need first to use integration by parts to get this estimate. And then you can put, let's go back, the big constant on this term and this small constant on the second term to get this estimate. So, so at the end, we can show by considering sufficiently small epsilon and applying the Gronwall lemma that this integral is equal to 0, which implies that u is equal to 0, and then also h is equal to 0. So these were some technicalities I tried to explain. If you consider general operator L, like in the original problem, so you need that asymmetric uniformly elliptic C should be strictly positive, the coefficient C, and we need also this information about the time derivative of A and the time derivative of the coefficient C. Okay, the proof is easier if you can show that effect, the time derivative of the convolution of k with u minus 0 belongs to this space. But in fact, we are not able to do this with the standard estimates we made. So, but if you assume this in the proof of uniqueness, can allow additional assumptions on the solution, then the proof is easier because then you can directly test with u of t, and you will only need to integrate once in time. And you can use this estimate on h of t, just assuming that f is globally Lipschitz continuous. And you need to use the result from Kobicha and Yamamoto and absolute continuity of the solution to obtain this lower bound estimate. So, and if you have this estimate, the terms in the height and side are easier to handle as well. So you get this at the end, this estimate here. So you need to fix epsilon smaller than k at final time divided by 2, and then you apply Gronwall lemma to obtain that u is equal to 0. And in the case of a time-dependent operator, you don't need assumptions on the time derivatives of the coefficients, only uniform ellipticity, and it's even sufficient that C is only positive due to this information we got on from the convolution term. So in the previous proof of the uniqueness, I obtained this information explicitly from the operator L, from the term corresponding with the coefficient C. Okay. So how did we show the existence of a solution for exact data? So we used the uniform mesh, idea is Rothe's method. You define time frame and uniformly. The time step is denoted by tau and is the number of time intervals. And you use backward Euler method to approximate the time derivative. And we consider this time discrete convolution approximation. So the kernel k is embodied at equal to 0. So for this reason, we shift the index to 1 to avoid this singularity in the kernel k. We defined that for I equal to 0, that this is equal to 0. And under the positive, if this k is a positive sequence decreasing and convex, then you can show that this has also the positive definiteness property. So the quadrature formula for a convolution structure is preserved in a discrete form. And so this we have used when making a priori estimate. So first you have to consider the formula on a single time step, Ti. You do this for every time step and using this approximations. So this is a convolution approximation. U as a solution on time step Ti. H is the value of H at time EI. And in the expression for H, we have considered the solution of U in the previous time steps. So this makes in fact that this problem at the discrete level is decoupled. We will first derive H1 from U0 and from the other data functions, and then having the value of H1, which is a real number, you will solve a discrete problem for UI in the H1. And this you do for every time step. Also here in the right-hand side, solutions of the previous time step are considered, which allows you to use the Lux-Milgram lemma to obtain a solution on single time step. So in Rothe's method, you have two main ingredients. You need a priori estimates and compactness arguments to obtain global existence of a solution. And the goal was to work with non-smooth solutions, but there's a certain restriction. We assumed that the convolution of k and the measurement in 0 is equal to 0. This is something important when you consider function t with exponent gamma. And you look at the convolution of k with its derivative and take the limit for t equal to 0, then this is equal to 0 if gamma is strictly larger than beta. But it's a finite value for gamma equal to beta. And sometimes often forgotten when making analysis in fractional PDEs is also that the solution, so the capote derivative, sometimes 0 is finite. If gamma is strictly smaller than beta, it's not defined. But we assumed that this is equal to 0, so we allowed for a measurement of this type, t to the power gamma minus L denoting the order of the derivative, but this gamma is between beta and 1. So it cannot be equal to beta, and this is what I would like to show in the future, that also for gamma equal to beta. So here in this lemma, it's written that there exists a unique couple UI-HI on every time step. And the second lemma you see is the first a priori estimate derived by Siskova and Slodichka. This one we could get it from their paper. But afterwards, they differentiate the equation. And in fact, they assume that this is equal to 0, which is typically not the case. So we use the positive definiteness of the kernel to show that this estimate is valid. So by testing with delta UI, so let's with the time derivative of the solution with a discrete analog, and we needed assumptions on the convolution of k with the measurement of its derivative as well, and also on the Neumann boundary condition to obtain this L infinity bound in time on the discrete solutions. And using, in fact, also the second, that the second term is bounded, we can use Kolmogorov theorem to show that the functions, function un bar here on this picture, which is a piecewise constant prolongation of the solution on this single time step, is has a convergent subsequence. On the right part of the figure, you see the linear in time spline un of the solution. So the idea of Roto's method is to prolong the formulation of the solutions on the discrete time step onto the whole time frame. And for the forward problem, I considered also a prolongation of convolutions in my paper in applied in AML applied mathematics letters, where I first time considered this convolution Rote function, which we also have used in this work. So the Ritz-Froschek-Kolmogorov theorem implies the uniqueness of a subsequence converging to U in this space. We have V converges in the H1 Sobolev space following from the reflexivity. And we have also weak converges for the H and Rote functions, in fact for a subsequence to some element H. And at the end, what you do is you show that U and H are solutions to the original problem. And this works. So in the case, the limit transition works fine. And for the uniqueness, we need that F is linear in U. So the results are, or the solution spaces are summarized in this theorem. In fact, we obtain that H is in L infinity and U is even continuous in dual sense. Okay. What's advantage about the graded match? In fact, in my opinion, at the moment is most has a computational advantage. It gives a better approximation around the initial time for the unknown source. So in the case of a graded mesh, you have exponent r here in the expression for Tg. So if r is equal to 1, you have a uniform mesh. Tau g is a difference between Tg and Tg minus 1. And here you see the L1 approximation on a graded mesh for the Caputo fractional derivative. So you use backward-Euler method on the time interval to approximate the derivative of u. And instead of using a shifted value of the kernel, you integrate this kernel, and this gives this coefficients ai, comma l, index il, which are defined here. So with the kernel g2 minus beta. So this approximation is denoted by d beta and ui. So we used in the convergence result this lemma out of a paper of Stein's. So under the typical assumptions on the solution, he showed that the truncation error is this bound, g to the power minus this minimum of this two exponents, 2 minus beta and r multiplied with beta. They showed that the optimal convergence rate for the mesh is 2 minus beta divided by beta. And the reason, if you take r larger than this value, or in general larger, this increases the temporal mesh around the final time. So this increases the error at the end, and you have need some balance between improved error at the beginning and decreased worse results at the end of the time frame. This is the discrete formulation for the gradient mesh. It looks like for the uniform mesh with the convolution quadrature is replaced by the L1 quadrature. And then you can make also stability estimates for this problem. We used non-uniform discrete fractional Gronwall inequality from a paper of Liao to obtain the bound on the norm of UI, which is given in this lemma. So this is bounds on the approximation of the Caputo derivative and on the norm of UI in H1 can be obtained under this classical assumption on the measurement. So without assumption on the solution. But then for the convergence of the scheme, to make the limit transition, I needed to assume that also the solution has the typical bounds. And it's something in fact, I don't like. I want to show that there is convergence without assuming properties of the solution. Or first you need to show that the solution has certain properties before using them. And also restriction, the gradient mesh parameters should be larger than 1 over beta, but this is the case for the optimal value. So I still have some numerical experiments to show. We considered this exact solution with here t to the power gamma. This is the exact form for h of t, where the other part of the source is a sine function. This is a measurement. And we consider different values for gamma, 0.9, 0, in the case beta 0.5, gamma 0.9, or gamma equal to beta. And then we consider 3 cases, 0.2, 0.5, and 0.8. For all experiments, the conditions for L1 scheme are satisfied, but not for the uniform scheme. These conditions are at the moment not satisfied. So discretizing problem in time, and at each time step you use finite element method with first order Lagrange elements. Consider 200 time intervals, the optimal value for the graded mesh parameter. When considering a non-uniform mesh, and in the measurement we have added in 100 pounds uncorrelated noise, and then as we need some well-behaving function as input in the scheme, we have regularized noisy data by nonlinear least squared method by considering a third order polynomial plus this power law to get some nice approximation, and we use this as input in the scheme. So I use Phoenix project for the computations, and here you see some results for first experiment for different noise levels. Black curve is the exact H. The other ones are the numerical obtained solutions. On the left you see for the uniform mesh, and here on the right for the graded mesh. So in fact, this situation is quite accurate also for a uniform mesh. When you look at the experience with gamma equal to beta equal to 0.5, you see the not so good approximation around t equal to 0. For the uniform mesh, if you use graded mesh, then the approximation is better, but still can get improvements. This is when gamma and beta are equal to 0.2. And here, if you get closer to 1 for both values, then the approximations become worse. For the uniform mesh, following my approach, the convergence is 1 minus beta. The order of convergence is expected to be 1 minus beta. So I think this is an explanation. You will need a very, very tiny mesh to get some better approximation. And also with this drawback is to solve the problem at time step ti, you need all the solutions of the previous time step. So also you need to save the solution, so it starts to become really expensive. And you also see for the graded mesh that there is a loss of accuracy. Also, the reason is also that the graded optimal graded mesh parameter also comes closer to 1. So I believe that is the reason for this behavior in the results. So I will shortly mention that we also have considered the multi-term fractional equation only on the graded mesh. Multi-term means finite combination. QRs are positive, betas are ordered between 0 and 1. We made typical assumptions on the solutions. We could show convergence of the similar scheme using this results of Huang and Steins, where you in fact have that the truncation error is for all beta is bounded by the one for this way by, and here you have the maximal beta. So here the optimal mesh parameter is related to this beta m, and also here the convergence under this condition. So this is the measurement formula with the noise, and we did something else. Here is we also considered a graded mesh for the measurement span. So we allocated more pounds at the initial time. At that time I was just taking specific values for R and 1, 2, 4. Later I realized that probably also optimal parameter for the measurement can be this optimal parameter for couple to derivative. So but here we saw that when you allocate more pounds around the initial time that you can get better results, but if R is too large, that the results are not necessarily improving. So for future work, I mentioned already some topics. So this restriction related to the measurement should be removed. This would be a very nice result. So the convergence graded mesh without assumptions on the additionally, as you also see from the approximations, in fact, the worst approximation is at the first time step. It would be good to find some way to improve this approximation at first time step, so it will also result in better approximation for the next time steps. Well, I don't see at the moment how it's possible to consider local measurement in connection with this problem in direct boundary conditions. So this would be also a nice direction for future research. So thank you for your attention.
Thank you so much, Karel, for the excellent talk. Any questions or remarks? Quick questions and remarks? Or?
Hi, Karel. Thanks for your presentation. My question is, did you realize any effect of the final time, especially if you choose the final time capital T large? Did you see any effect to the reconstruction process?
I've not considered. I took the experience equal to 1. So, but the results are the existence results are general are valid for finite time t. Normally, if final time becomes larger, you will need an even more tiny time step tau. So it will increase at least increase complexity of the problem to get the same accuracy. If t is 0.1 or 0.01, you will also be able computationally to get with less computation cost good, maybe better approximation. But so
I understand that you use the same mesh for measurement and the reconstruction. Am I right?
Yes.
Okay.
But different time time points for measurement, and then for the numerical scheme, I considered 200 time points for measurement, only 100 But then it's approximated by this non-linear least squares method, so you get a function that is defined on the whole time frame, and you can use any value of it.
Okay, thank you.
Thank you, Onur.
Okay, any other questions or comments?
I have questions, but I may ask at the end if there are some other
We have
questions.
very limited time, Aliur.
Okay, only one question then. You used Caputo derivative in the problem. Was there a particular reason for that, or for example, would you get different results if you use, for example, I don't know, Riemann-Leibel fractional derivative or something else?
I consider Caputo derivative because then you can use the initial data, the time 0, and not you need to, not an integral of initial data. And I think from practical side, this is more appropriate to consider to use U at
And
initial
also
time.
perhaps convolution. I thought I have no idea about the structure, but perhaps the usage of convolution might be a reason. Hocam, Ayça Hocam, I have some other questions, but since we have limited
Aliur,
time.
I am so sorry. Nebosha has, we have to end because of the Nebosha schedule. I'm so sorry.
It's okay.
But you can send me
But
an
you
email.
can, yeah, just send an email to Carol,
Sure,
please.
Sure. Thank you.
Okay. Then Carol, thank you so much again. And
It was a pleasure to present my work.
thank you, Carol. And thank you very much, everyone, for joining us. We are gonna see you in 2 weeks again, I hope.
Thank you. See you.
Thank you so much. See you.
Thank you.
very
Good
much.
day.
Bye.
See you.
Bye.